it's time for the lecture. So today we are very pleased to invite Dr. Figueroa Romero, and he is now at the Hong Hai Content Institute. And Dr. Figueroa Romero, he is from Mexico, and he received his doctor degree at Australia Monash University, yeah. Right? Yeah. In 2000.
Last year. 2021.
Then after his PhD degree, then he came to Hong Hai, and this is the first postdoc for him. And so today he's going to talk about this randomized benchmarking for non-Markovian noise. So let's welcome Dr. Figueroa Romero. Okay.
Thank you very much. It's really nice to be giving a talk again in person. It's the first talk that I give in person since a couple of years ago. So yeah, it's really nice to be here. So yeah, I'm going to be talking about randomized benchmarking for non-Markovian noise. So the topic is roughly quantum computing, benchmarking quantum devices. I realize now that I made my slides maybe a bit too technical. So you guys, please feel free to stop me at any time and just ask any questions. And even like if you at some point zone off in some of the topics in the technical details, please just don't try and get lost trying to figure out if you're unfamiliar with something. I'll try to explain things in a rather simpler way. So first, I just want to acknowledge my collaborators. So Minxu Xie, he's the leader at the Foxconn group in Taipei. Kavan Modi was my supervisor in my PhD. He's the expert in quantum stochastic processes that I'm going to tell you a little bit about. Tom Stace, who is at the University of Queensland, and now he's at Q-Control. Rob Harris, also at the University of Queensland. And Felix Pollock was my co-supervisor. So yeah, these guys contributed a lot to all the stuff that I'm going to tell you about today. So just to give you a rough idea of what this talk is going to be about. So it's going to be about quantum devices, and specifically about the goal of having useful quantum devices. So we know that we have a lot of different technologies being pursued right now. And all of these have in common that we want them to be of general purpose, right? We don't want them to just do one single thing good and that's it. We want them to be a bit more general, to have a wide set of applications. We want them to be accurate, of course, and we want them to be scalable. Okay, so those are the goals. And I mean, all of them present some challenges, but right now, errors or noise is really the worst problem affecting quantum computing today. Okay, so what does noise mean? So here, noise means that you get some experimental outcomes, and you can think of these outcomes as deviating from some ideal result, as if you send those ideal samples through some noisy classical channel. Okay, so that's what the way that we can think about it. Of course, physically, there are many other things happening. I'm not going to go into the detail of what little things are happening, but I'm going to give you some idea of roughly how to quantitatively look at these sources of errors and types of errors. Now, despite this problem with noise, there is this thing called the fault tolerance theorem, which basically says that you can compute reliably and indefinitely with a little low overhead, so with very little resources, if and only if you have, so this is a sufficient condition that the theorem states. If your errors are below some threshold, some small probability, and if your correlations within the noise, within the errors, are sufficiently weak. Okay, so this means that if with very small probability you will get some error, then you below some threshold, then you can compute indefinitely and reliably. Then if correlations are sufficiently weak, so if the noise kind of doesn't propagate too strongly, then you can compute without a problem. Now the issue that we have now is that these thresholds that people have looked at experimentally are very low. So we're still very far of reaching those thresholds. And the correlations, as we try to scale up these quantum devices, as we try to put more and more qubits, these correlations become really important. Now, the thing with quantum devices is that you cannot just get them out of the shelf. It's not that you can just go and grab a quantum device. You have to kind of constructively build them. And so this requires several steps. The thing is, first you gotta prioritize what kinds of things you wanna look at and what kinds of errors you're getting. Then you measure things, then you measure things and then you see, well, I'm getting these types of errors and so on. Then you fix those errors and then you verify that you're getting the right answer. And then you go again, you prioritize some kinds of errors, then you measure, fix, and so on. And that should take you eventually to some fault tolerance. Now, generally we need some precise characterization and control of quantum devices and of these types of noise. And the first step, so when I say benchmark, I mean to put some kind of reference of how noisy these quantum devices are. And that is a very first step that we can do just to estimate, well, what's going on. So now the gold standard to begin this process is called randomized benchmarking. And I try to emphasize to begin because randomized benchmarking also has a lot of issues. But it's the best thing that you can do. And it's actually what people always do at first when they try to benchmark their devices. And I'm going to tell you specifically what randomized benchmarking is. But for now, you got to know that it estimates average error rates of some gate set, of some set of quantum gates. It requires very little resources, so you can do things without too much complexity. It is insensitive to state preparation and measurement errors. So you just benchmark the gates that you're applying in your computation. The state preparation measurement errors doesn't affect that. And it gives high confidence in the sense that the variance of the data that you get is pretty good. It's kind of tight. And now what I was telling you about randomized benchmarking not being like the perfect benchmarking tool, it's because, well, it really requires very little resources. But it also gives you kind of not too much information. It just tells you the average noise that your quantum device has is this. Okay, and that is usually what you see people reporting when people say, oh, my quantum device has 99.8 fidelity or something like that. That means they did a randomized benchmarking, or well, it most probably means they did a randomized benchmarking experiment and they got some average fidelity of a given percentage. Okay, now there are many other techniques that you can use, but these ones, they will give you more information. Okay, they will tell you more about the types of errors that you're having, but they also have a higher complexity. So for example, this technique called gate set tomography, for example, or quantum process tomography, it tells you everything about the noise, but it requires a lot of resources. Okay, getting confused with the okay. But just within randomized benchmarking, so it has been around for like 10 years now, or perhaps even a little bit more. And there are many different flavors of randomized benchmarking. So depending on specifically what you want to look at, so for example, if you want to look at error rates of a whole gate set, or error rates of individual gates, or different kinds of purposes, you can take some of these techniques. It also depends, for example, on the gates that you want to benchmark, or on the types of assumptions that you do about the noise. You can use some of these techniques. Okay, now within all the types of different things that you can consider when you do a randomized benchmarking experiment, as I said, there are these assumptions on the noise. And whenever we assume, so I'm going to tell you what Markovianity means and non-Markovianity. But whenever we do kind of simplistic assumptions on the noise, so for example, when we assume Markovianity just means that the noise doesn't have a memory. So it doesn't remember, for example, an error that happens when you apply your third gate in your computation, doesn't know about which error happened in the second, when you applied your second gate and so on. That is what Markovianity means, forgetfulness. Okay, time independence means a more general kind of independence of, it doesn't matter if you applied your gate now or if you applied it 3 seconds after, or yeah, it's a more general time independence. And gate dependence, yeah, well, okay, gate dependence, we know a big deal about gate dependence when we have Markovianity. So gate dependence means that the noise depends on which gates you are applying. Okay, and that is the more realistic type of error that you can get. Now, when you relax this Markovianity assumption, and when you take it together with gate dependence, then that's when yeah, all chaos kind of breaks loose. Okay, and most techniques, the problem is that most techniques that we have devised until now are made for Markovian noise. Even if people sometimes don't tell you, sometimes they are implicitly assuming that the noise is Markovian. Okay, so now I'm going to tell you in a little bit more detail what the randomized benchmarking protocol says. So suppose you start with some initial state raw that you experimentally can prepare. Then you sample a number n of gates that you wanna benchmark. So these quantum gates are just the operations that you wanna do in your computation. And so the gate set, the only restriction on the gate set is that you should be able to compute the inverse of the whole sequence of gates. So suppose you apply G1, G2 up to Gn, and then you should be able to obtain the inverse, the sequence of inverses of those gates. So that is the only restriction. There are some protocols that go around, that get around this inverse restriction, but I'm not going to cover that one in here. This is the kind of standard randomized benchmarking protocol. Now the problem is that, the deal with randomized benchmarking is that if you were to apply ideally this inverse, then you would just get an identity, right? It would be as if you had done nothing. But the problem is that doesn't happen. So then you can say, well, let's model this noise that we're getting as applying your first gate and then getting some unwanted map after your gate. So this map where I say here CPTP, if you don't know what CPTP means, this just means it's a physical gate. Okay, this means completely positive and this trace preserving. If you don't know the details, it just means it takes quantum states to quantum states, preserve probabilities. So yeah, it's just a physical map. So you can just model things in this way, and then so because you're sampling these gates uniformly at random from the gate set, you can just do this. Well, first you measure some PUVM element, so some observable, and you estimate the probability of getting a certain outcome, for example, or if you think of some observable, for example, the projection on your initial state. Suppose you start with the ground state, and then you just measure the projection on that ground state. Then you can just estimate this expectation value after you perform this computation. Now, what I wanted to say is that, well, you can do this several times. because you're sampling these gates at random. You can just do this many times and estimate this average, so this average of these probabilities, and just get statistics and study what happens when you start increasing the sequence length. Okay, we usually refer to this quantity, this average, as an average sequence fidelity, even if it's not exactly a fidelity, but we can relate it to some quantity that is known as gate fidelity. So this gate fidelity tells you how good your gates are, or how far they are from identity. So these lambdas, these lambda maps, the gate fidelity tells you, well, how far are these guys from the identity. Okay, so if you have a really good gate fidelity, it means that these guys are almost the identity, so they are not really taking you far from your ideal gates, from these guys. Okay, and yeah, as I said, well, so the statistics that you will get after you do this many times will depend on which assumptions you make for these guys, for the lambda, for the noise maps, and for which gate set you are sampling from. So these guys, depending which gates you are sampling, the profile of the data that you get will depend on that. Now, this is kind of one of the most simple cases that you can look at. So you can assume, okay, so Clifford as well, if you don't know what the Clifford gates are, it's just one kind of quantum gates that you actually, they are not the gates themselves, they are composed of other smaller operations. So yeah, if you don't know what these are, don't worry about it. They are just some special kind of gates that you can simulate efficiently. So that's why people look at these gates. And then if you put these extra assumptions, then, so Markovianity, gate independence, and time independence, then the data that you get looks like this. So it just looks like an exponential decay. And then the theory is also super simple. In the end, if you compute that average analytically, then you just get something like this, where this p is just some number between 0 and 1. And that tells you that this thing looks like an exponential decay. Okay? And now this p quantity in here, the point of randomized benchmarking is that you can relate it to the average gate fidelity of the noise. And that tells you, yeah, about how good your gates are. Okay, now this is again some detail. So yeah, in the end you compute this thing analytically. So this E just means analytical average over sequences. So you basically average over like different types of gates that you can have. And this P, in turn, you can relate it to this quantity, which is the average gate fidelity, which looks something like this. Then, again, if you're not familiar with this, then don't worry about it. The point is that these constants, A and B, they get all the span errors, so all the state preparation and measurement errors are contained within A and B. And that's why they don't affect the decay, and they don't affect whenever you want to extract the average gate fidelity. It doesn't matter what these guys are. Okay, now again, this is also a technical slide, but we can do this. So we know now that we don't have to assume that the gates are Clifford. We can extend this to any finite group. So I guess the restriction with these gate sets being a group is that you need the inverse, and that's really the biggest restriction of why these guys have to be a group. So this gate set G has to form a group. But when you relax it, so when you relax the gate sets to form a group, then we have some results that let us compute. So this twirl is just like an average. Yeah, again, if you're not familiar with what this twirl is, so this guy just looks like an average. So this is 1 over the cardinality of the gate set. So it's like doing the an arithmetic average. You kind of just sum over probabilities. So this would be like the action of this guy, which is a representation of your gates. So it's like saying, well, the gates look like, you take some representation and then you compute. So you compute this average. Yeah, this is slightly technical, so I'm just gonna move forward. The point is that we know how to do this thing more generally. And yeah, in here, so we can apply this technical result, which it's not Schur's lemma per se, but it relies on Schur's lemma. It's like an immediate consequence of this mathematical result called Schur's lemma. And the point, when you relax this thing on the gate sets to be just a group, a finite group, is that you, instead of getting a single exponential decay, you get a linear combination of exponential decay. Okay, so this is slightly more general, but still you get this kind of benign behavior in the data. And again, the span, so the state preparation and measurement errors doesn't really affect the decay, so they just go into this constant A. Okay, and this F, so they contain the gate fidelities, so how big this lambda is, the noise, so how bad it is. It's contained in these F quantities. Okay, and this sum is then again over different irreducible subspaces of your gates. Yeah, this is again a kind of technical thing about group theory and so on. The point is that so instead of getting in the Clifford case, your noise just goes to either it goes to one sector or the other, so you just get A P times M, P to the M plus B. So it just goes to those two terms, whereas in here it can go to several terms, okay, quantified by this pi. So this pi can run over 1, 2, 3, 4, 5, depending on which gate set you took, you can have as many terms in here, okay? So you can have several of these quality factors F. Okay, so in here they're called quality parameters because similar to the Clifford case, they quantify or they are related to the quality of your gates through the average gate fidelity. Okay, so I hope the idea is more or less clear, even if the whole detail I guess it's yeah, a bit technical, but I hope the idea is clear. Now this is all within Markovianity as well, so I haven't even told you what non-Markovianity is. But furthermore, so now, again, within Markovianity, if you try to relax this gate independence on the noise, if you try and say, well, suppose your physical gates, so these are the gates that you actually implement in reality. If these physical gates look like your ideal gate after some noise after your ideal gate. So suppose you apply your ideal gate and you get some noise extra after that. And then you get some contribution that depends on what gate you apply. Okay, so gate independent would be only this guy, okay, without this delta term. So suppose you now have this contribution, then we know, so these guys since 2017 until 2019 have refined these results. We now know that this average sequence fidelity just looks like the gate independent term plus some little contribution that itself decays with sequence length. So this M, remember, it just tells you how many gates you're applying. Okay? So this M, for example, if it's 10, then it means that you apply 10 gates and then just try to invert the whole sequence. Okay, so this is, okay, and these terms, so we know that at least for physical noise, this delta 2 term will be small, okay? So this perturbation, this will actually be a perturbation term, so it will, in most cases, be a kind of small term. So you would see the data, instead of being just an exponential like this, you would get something like a little bump and then decay exponentially. Okay. Now, okay, so all of these things that I've told you is within the Markovianity assumption, but I haven't told you exactly what Markovianity means, even if I gave you a kind of broad idea. In general, yeah, so within quantum mechanics, so classically, we know very well, and people have studied what Markovian and non-Markovian processes are, like very in a lot of detail. But within quantum processes, it gets a bit trickier. So it's still, I mean, even the field is kind of contentious still. But generally, so what it means is that, yeah, just some process that depends on the full history, as I kind of told you a little bit before. So you can think of having, so think of this line as some Hilbert space, and then you apply some gate A naught. Then the dynamics happen in here in this line. Then you apply some extra, some other gate A1. Dynamics happen and so on. And then you apply some final gate AK minus 1. Okay, and then you measure in here. And then you can tell, well, if your statistics are what you expected, or if there is some memory kind of hitting you back after you applied all this. Okay, so that's roughly what it means. It just means that processes have a memory. Okay, now classically, you probably already know about this equation. So a classical stochastic process is Markovian if it has no memory. So it means, suppose you have some classical random variable x, and at some point k, you want to look at the statistics of getting some outcome k, xk, given that you obtain outcomes xk minus 1, xk minus 2, and so on until x1. Okay? Then if the process is Markovian, your outcome at the next step, so at the step k, will only depend on the previous outcome. Okay, so that's the way that classically we can express what Markovianity means. Now, to give you an idea of why this matters, or why this is a massive simplification, is that if you use this definition of conditional probabilities in terms of joint probabilities, then you can realize that the joint probability of some process of length k will depend only on 2-point probabilities, conditional probabilities, so only 2-point correlations, okay, if you have this Markovian assumption. Okay, if you don't have it, then you have to know all these conditional probabilities, okay? And that is, so the complexity scales exponentially. So that's why Markovianity is a massive simplification. And the other point that I want to make is, if you want to talk about non-Markovianity, you really have to talk about multi-time higher order correlation, okay? So only 2-point correlations won't really do it. And I mentioned this because this has been the approach in open quantum systems for a while. And it's not, so I mean, it can tell you when a process is non-Markovian, but it's still not sufficient to tell you more about the process, or it can fail. Like it might not know when some process is non-Markovian. So it's just an insufficient approach. Okay, so really you have to turn this approach of open quantum systems to a multi-time approach. And also, so just to give you the physical picture, because I didn't mention it probably, the physical picture is the environment. That's the thing that serves as a kind of memory. Okay, so essentially you get some interaction between a little system and the environment, and there is some information flow with the environment. Okay, so you can think of the environment as some kind of memory that holds the information that happened before, and then it can send it back to the system. So okay, this slide is just to give you an idea, or just to tell you that there is a very formal way that people have devised to study this generalization. And the main object that I'm going to talk to you about is this process tensor. I'm not going to give you all the detail about what this is, but yeah, this is just to give you an idea. And so the way that we think about non-Markovianity, of describing non-Markovianity, is, well, now you have your system, so these lines, just think of them as some Hilbert space. There is no sense of time in here, so, but I guess, you know, you can read this diagram from left to right. These are the Hilbert spaces, so suppose you have some system and some environment. Your initial state can be correlated between system and environment. And then what you do is, well, to describe a quantum stochastic process, is you can act on your system. So this system is accessible to you, but not the environment. Okay, so that is kind of the assumption that you don't have access to the environment. So then you can apply some operation in your subsystem, this A1. Then some dynamics happen. So this is closed system dynamics, okay, between in environment and system. So just think of Schrodinger kind of dynamics in here. Then you can apply some other operation in your subsystem. Then you have dynamics and so on. Okay, and then you can measure something, right? Then what happens is, well, you can get a kind of, well, not a kind of, but a generalized Born rule. So you can see, you can gather all the multi-time statistics in here just by running this kind of circuit. Okay, and the idea, or the way that we can generalize this notion of non-Markovianity to the quantum domain is just to think of all the underlying, so all the stuff that you don't have access to, and even the initial state, you don't have access to the initial state, right? You can just apply preparations and try and prepare some initial state, but you don't really have access to the full state. Now, you can gather all the stuff that you don't know in some multi-time higher order tensor that we call the process tensor. So this is just a map that you put some operations in here, and then it spits out a quantum state, okay? Just in your subsystem. Now this object has also like all the properties, and you can define this thing mathematically also rigorously. Like I just showed you a cartoon, but you can define these things. And people have looked at it, so they have looked at similar objects, or essentially the same object, with different purposes, and yeah, we know them by different names, but it's essentially the same kind of object. This is a little bit of a, well, yeah, I would prefer if they just knew it, we all knew it as the same thing, like with the same name. But yeah, we know it by different names depending on what kind of topic you're studying. But now, okay. So the point in here, if you don't know what choice states are, don't worry about it. You can. The point is that you can just do some contraction. So you can gather all the operations in here that you did, which can also be correlated with themselves. Okay, so you can have some information traveling here, and you can correlate your operations if you wish. And the point is that you can also gather this object in some kind of multi-time higher order tensor, and then just do some contraction of these two, and then you just get your outcome at the final step. Okay, and now this is as well just to tell you that so we have a specific operational condition for Markovian quantum processes. So kind of the equality that I showed you before in the classical case of probabilities not depending on all the previous outcomes. We have a similar condition for quantum processes, which you can find just in this paper. And in particular, one of the implications is that Markov processes just look like uncorrelated processes. Okay, so you can think of, you would just have your input state in system, and then you would just tensor that with some quantum map taking you from the first step to the second step. Then you just tensor another map taking you from the step 2 to the step 3, and so on. Okay, so uncorrelated objects are the easiest ones to deal with in quantum mechanics. So and in the end, you also get a nice simple well, simple, because to compute it's really, well, it depends on which distance you choose. But you can just define some simple non-Markovianity measure as the distance. Okay, so you can choose whatever relevant distance that you want in here between your quantum process, the process that you want to quantify non-Markovianity on. The distance with Markovian processes minimized over Markovian processes. So just the distance from your process to the closest Markovian one. Okay, so think of the space of processes, then you just look at how far you are from the closest Markovian process, and that's a measure of Markovianity, of non-Markovianity. Now, for randomized benchmarking, so the story that I told you before, randomized benchmarking is just this, okay? So Markovianity just means that the gates act locally in here. There is no information traveling from here to here, okay? So in that sense, there is no memory. Whereas in the non-Markovian case, we would have something like this, okay? So the information from what this guy was can travel here to here, okay? And then it can travel from this one to the other and so on through this environment, okay? And that is really nice, because then we have the mathematical machinery to deal with this. Again, this is technical. You can take the average over these guys. Yeah. The point is we can do things, okay? Now, this is what we did in this last paper that I had in the cover of these slides, in the first slide. And we can generalize this twirl that I showed you before, that I told you that it's a kind of averaging. We can generalize this averaging to when you do the averaging only on the subsystem. So when you don't have access to the environment, we can actually do this averaging by letting this twirl guy, so this average guy, act only on the subsystem part of the noise. Okay. This is technical. The point is that you can gather all the noise in the system part. Okay, and the point is that in the end, you can do this averaging and you get some quantity that looks like this. Okay, so these are just projections on subspaces of the gate set that you are looking at, or the group that you are looking at. So remember, in this case, I'm talking about doing randomized benchmarking with finite groups. Okay, so it's a generalization of the Clifford randomized benchmarking. And yeah, the point is that you can get some object that, so this guy is kind of the generalization of the quality maps that I showed you before. So the quality maps that tell you, well, how strong or how bad your noise is. This is a kind of, it is a generalization of those objects, and now they depend on this environment. Okay, so these guys, these E prime, epsilon prime, these are just environment dependent quantities. Okay, so again, yeah, this looks very ugly, but the point is that the qualitative picture is sort of easy. Okay, in the sense that those guys capture all the noise. Okay, now this average sequence fidelity, the object that I told you, you gather statistics from randomized benchmarking and so on, now just looks something like this. Okay, even if it doesn't look like the exponential that I showed you before, it's almost in that form. And now the relevant objects are these guys, so these Q terms. Okay, so in a randomized benchmarking of M quantum gates, you would get something like this. Okay, which is really ugly. But if you have seen tensor networks before, maybe you'll realize that, well, this ugly thing just looks like something like this. Okay, so it's like a matrix product operator contracted with these projector guys. Okay, now these projector guys, I think I also didn't mention, but these projector guys just depend on the gate set or the group that you are benchmarking. Okay, so if you decide, I'm gonna do randomized benchmarking for this particular group, then you'll get some projectors. Okay, so for the Clifford group, you just get 2 projectors. Okay, and then you can just compute this quantity, and you get the exponential decay and so on. So these projectors just depend on which gate set you decide to benchmark. Okay, and the point is that this quantity, even if it looks ugly mathematically, it's just really some contraction of tensor network or of matrix product operators. Now, that was one result that we got in the paper that I showed at the beginning. And in the end, in the paper as well, you can see the detail of how this thing reduces. So these quality maps reduce, in the Markov case, reduce to this kind of product of different quality factors. And when the noise is time independent, it reduces to this power to the m of the quality factor. Okay, and furthermore, if you have Clifford gates, this guy will be just the p to the m. Okay, so the noise strength to the m, to the number of gates that you have. Okay, and for the ASF, so the average sequence fidelity, this f guy, it reduces as well to the known case. Okay. Now the Clifford Group, again a technical slide, so I apologize for this, but just to so that you know what the Clifford Group is, I just spelled it out like this. So it's a stabilizer of the poly group on Q qubits. Specifically, it has to be multi-qubit Clifford Group. Okay. But then again, that's a technical detail. As I told you, for this Clifford Group, you get two irreducible subspaces. That means you get two P's. Okay, you get one P and second P. So these projectors just have, well, this form where this guy looks like a maximally entangled, or a projection with a maximally entangled state. Yeah, this is just a detail. You can see that things reduce to the nice exponential case when you take the Clifford Group and Markovianity and so on. So this is because we studied the case of the Clifford Group in this paper last year. So this is on PRX quantum, and we did a lot of numerics and we studied it in a lot of detail. And you can see that you actually get these kind of deviations from exponential. So these points, the points with bars, are numerically generated. And the red curve is the analytical curve that we got. Okay? And this dashed line would be the Markovian, like the Markovian counterpart. And when I say Markovian, is you kind of cut the wires in the environment. So in this drawing, you would just cut these environment wires. Okay, so no information would be traveling from here to here. You just cut these guys. And you just get, yeah, this exponential decay. Yeah. Yeah, so this is just an example, and it's actually not a very physical, because it would mean that the system and the environment would be interacting very strongly. So this is just one qubit as system and one qubit as environment. And they would be interacting, yeah, with noise, that it's an exponential of this, well, yeah, with this Hamiltonian. And yeah, I don't think, yeah, the noise, yeah, we kind of just engineered it, like we came up with it, just to give an example. Yeah. Also, so for example, this is unitary noise, which is also a bit not really that great to study with randomized benchmarking, because there are some other issues with so this would be coherent noise, and yeah, randomized benchmarking is a bit problematic with coherent noise. But yeah, this is, in this paper there is a lot of detail with other numerical examples as well. Okay. So one case for this result is fabulous from step to step within the noise. And the way that we model this, or that we thought, well, we can model this with this kind of noise. So this would be the noise at every step. And suppose you have some Q between 0 and 1, then this gamma would act on system and environment. And then you have another contribution where the noise is this phi, and it only acts on the system alone. Okay? So you can think of small non-Markovianity in this case, or modeling, or being modeled in this case, for a small q. So for example, if this q is 0.001, then that means that almost all the contribution is in this guy. Okay, so almost all the noise is only on the system part. Now, when you take the noise in this form, then you can get some type of expansion. So this is more like a binomial, well, a multinomial expansion in Markovian contributions. So it looks just like this. In here, I haven't assumed that Q is small or anything. I haven't done any approximations. But this becomes a non-Markovian expansion when this Q is really small, as I told you before. Yeah. Now, the other problem is, well, how do you operationally, so once you did the experiment, then how do we extract what this quality map is? Okay, and that is a massive problem, because in the Markov case, you can just do a fit of the exponential, and then you extract what that P parameter is, and you can get the average gate fidelity. Okay, but in this case, you don't get an exponential. You just get some ugly curve with bumps, as I showed you before. And then, well, how do you extract this quality parameter? And we noticed that, well, we can just gather all the randomized benchmarking process in this guy. Okay, so this F acting on some gate would look like this. Okay, and then you can just say, well, this is where randomized benchmarking is. And now, if we average over initial states and measurements, we kind of can break, well, or can get inside of this guy. So we can extract some information about these guys. Okay, and that just means, well, suppose your initial state, you start with some ideal target, okay, and then you randomize that ideal target, and you get some noise as well. Okay, so this N can be some noise. Okay, and you do the same with your measurement. Okay, you start with some, so this would be some basis vectors. Then you randomize those guys, and you get some noise after that randomization. Okay, now if you average over these guys, you get something like this. Okay, so you again, this is not an exponential anymore, so that's why I put these parentheses in here, because this F depends on the sequence length, on how many gates you apply, but it's not an exponential. Okay, I'll show you what it is. But then you just get this simple term in here. Okay, this is average gate fidelity of this guy. Okay, now specifically or explicitly, it just looks something like this. Okay, so it's still kind of ugly, but we can already work with this, as I'll tell you. So you get this information about this guy in this term. Okay, and then we can extract information about this guy, as I'll tell you. This AB just contain span information, so how good the overlap is with your states, with your target state. Okay, so now a crucial difference now is that this average gate fidelity is a gate fidelity of the whole process. Okay, so in the Markovian case, you get just average gate fidelities of like individual contributions, whereas in here you cannot do that. Like you get the gate fidelity of the whole process. So how good is that process to being an identity? Okay. Now then, well, yeah, this is a technical thing as well. You can isolate each irreducible subspace by something called character RB. So this is a technique to isolate each section of these irreducible subspaces. It's a technical detail, but yeah, the point is that we can get each pi in the average gate fidelities. So in here, okay, ideally you would have this overlap to be 1. The problematic case is this one, because then it means that this guy, so one of these guys becomes 0, or this full quantity becomes 0, so that's why it's problematic. But then again, these guys are, it's up to you to pick them up. So yeah, you wouldn't really pick them up to be this. And that is true as well in Markovian randomized benchmarking. This is a technical detail. The point is that we can get, through this quantity, we can get information about this guy. Okay, in the Markov case, doing this average is redundant. You wouldn't get anything new. Okay. Okay, I think I'm almost done. So now, this is actually, I think, my favorite result. And it is that in the Markov case, these fidelities have this kind of modularity, in the sense that if you have time-dependent noise, in the sense that the noise is changing between steps, but it doesn't have a memory per se, in that case you can compute, well, how well or how bad is the noise between a given arbitrary sequence length. So say I want to see how bad the noise was from step 5 to step 11, okay? And you can do that because you can just compute this ratio, and then you get some quantity outside, okay? And that tells you, well, you get, so this will be some number between 0 and 1, and that will tell you how good your noise, how bad your noise is. Okay, and this is not possible to do in non-Markov randomized benchmarking, as I told you, because, well, you have dependence through all the steps. You cannot just isolate a particular step. Okay, but now, okay, in this case, in the Markov case, so that led us to think, well, in the Markov case, so because this guy cannot be greater than 1, a clear flag of non-Markovianity would be that you get this quantity greater than 1, okay? This is not possible within Markovianity because these guys are between 0 and 1, okay? So if you get, in the plot that I showed you before, the exponential kind of decay, if you get some exponential and then you get some bump that actually increases the fidelity, then that means that the noise cannot be Markovian, okay? You can get kind of wiggles and so on, but if you get a bump, I mean, wiggles already tell you that you have non-Markovianity, but if you get some increase in the fidelity, then that is for sure, like, there is no other way. Okay, that is a violation of this assumption. Okay, so then this led to the question, well, can we deduce something if we look at this condition? And okay, the one sufficient condition would be that these guys, so the difference between these quality maps to some n greater than m, if the difference between this guy and this guy is positive semi-definite, then you would see those kinds of jumps, okay? And a necessary condition would be, so even this quantity, so this is operator norm. If you're not familiar with operator norm, it's fine. This just means that, so you can interpret this as the purity of the intermediate state having to be increased by the square of this guy, okay? Technically, operator norm is greater singular value, at least for these matrices. But in here, like, physically, you can interpret this as the purity being increased by the square of this quantity. Okay, this is just a technical detail. And then, okay, this what I told you about, that the noise has to increase the purity by this guy. Okay, this would be just a product of this operator norm. Okay, and this already rules out coherent noise, so unitary noise. You need to have some other quantum channel acting as a noise. Okay, it cannot be, so coherent here just means unitary. Then furthermore, you can use this inequality to see that it implies that the environment dimension has to be at least of this I think this one is dying now. It has to be at least dimension of the system. Okay. So that just means that you need to have this environment, yes or yes, to have non-Markovianity. Okay. So okay, now I'm almost finished. We also wondered, well, can we say anything about gate dependence? In the end, gate dependence is also just a kind of non-Markovianity, so it's a kind of memory of what gates you applied. And there is this result by, so this is the result that I told you about by Joe Wallman, where you just get this extra perturbation. And we checked that, well, you cannot really do this. You cannot just get some extra term in the gate dependence sequence fidelity. And the main point, or the main reason why you cannot do this, is because the gate dependence gets carried with the environment. Okay, so in the environment, when you do the mathematics and so on, you get some contributions, so you get some map, some quality map, which carries the gate dependence, and you cannot just put that into a single perturbation. Okay, nevertheless, we could show that if you do some small, if you just have some small gate-dependent contribution, you can at least say something about your average sequence fidelity not going too far from our expression. Okay, that just means for some epsilon satisfying this thing, you get the difference between average sequence fidelities being less than that quantity, and similar for variance. Okay, so this is just variance of the sequence fidelity. Okay, so now I'm just gonna wrap up. Sorry for all the technical stuff. I hope at least the idea is more or less clear. So yeah, mainly non-Markovianity is challenging in general. I try to give you an idea of why non-Markovianity in general increases complexity. In particular, yeah, within quantum device characterization or noise characterization in quantum devices, there is a need, like almost all techniques to do this, make an assumption of Markovianity, and that is a problem when we try to scale up quantum devices. So when we start getting more and more qubits or circuits which get more and more, which get deeper, then that will become a problem, because you almost for sure gonna get correlations between time steps. Okay, and yeah, we established this framework where you can actually generalize and provide extensions to other characterization techniques. So in the near future, we want to incorporate this context dependence. So context dependence just means that the noise would depend on what is happening outside. So gate dependence would be a kind of context dependence. But yeah, we want to generalize this kind of gate dependence. You can also find grain, this thing. So for example, the specific purpose techniques, extracting these quality maps, doing, for example, different gate sets. We didn't put, for example, any structure on the gate sets, but sometimes quantum, for example, yeah, all of the quantum machines, they can just do very basic operations, and then with that you build bigger gate sets. But if we could benchmark directly these smaller operations, then that would be really ideal. And how to incorporate other time dependence, such as drift. So this drift means you go and you do your randomized benchmarking experiment today, then you do another one tomorrow, and the data is different. Okay, so how do you make sense of that? So that is kind of an idea of what drift means. And there are further questions. So one is mitigation of non-Markovian errors. And if we can use non-Markovianity as a resource, something that can help you rather than harm you. So yeah, there is people. So now Shixian Yang is working on that. Well, we are working together on topics similar to this one. And that's it. Thank you very much. Yeah, I usually put this as an advertisement for Taipei, but I guess you guys all know Taipei very well. But there are available positions if anyone wants to contact Somin Shu, the leader of the group. And also, if anyone wants to present some of your results, you can just send me an email, and yeah, we can have you at our seminar. So yeah, thank you very much.
So thank you very much for the nice talk. So now it's time for question and comment. So Ida.
Thank you for a nice talk. And I have a question. Could you go back to any page you have you represent the average fidelity in superoperator form? Like that. Yeah, like this one. So I'm just wondering, is it necessary to assume that the M operator to be a projector? Because if we prepare the initial state in the pure state, then it is obvious that if we want to obtain the average fidelity, we have to the M operator is the projector corresponds to the initial state. But what if the rho S is some kind of mixed state? For example, if it is entangled with other parties, then this like this, how do we define this M operator?
Yeah.
Because if we want to write the average fidelity in this form, I think there like M must to be a pure state or a projector.
Okay, so M can be any PVM element. So PVM element is, you can think of it as the generalization of observables. Mm-hmm. So it can be, it's not restricted to be a projective measurement. But in the end, you're right that you, like the choice that you make, actually, this is a choice, and if you make a bad choice about what your initial state and your measurement would be, then yeah, it would be harder to interpret your experiment. So yeah, ideally, some people even say, don't even bother saying, well, you have some rho S and some measurement M, but they just say, you start with the ground state, so the zero state, and you measure the projector on the zero state, and that's it. Maybe we should have done that, because yeah, I mean, you're right that, I mean, this choice, and as I said, for example, with this last bit, okay, so for example, if these guys take certain values, like 1, for example, or 1 over ds, then, you know, you don't really get any information. So yeah, this is a choice, in the end, yeah, this is a choice that one has to make sensibly for the experiment to make sense. Yeah.
Okay, thank you.
Any other question, comment? I have one question. So, you know, we know there's some, you know, available machine in the cloud, for example, IBM, for some qubit. They already have some, you know, non-Markovian noise. So, have you ever tried to apply your theory to real, you know, this machine and to test?
So we would like to actually either carry out an experiment and just see if there is non-Markovianity, or try to engineer some non-Markovian noise. In the sense, for example, engineering this evolution, these lambda maps as some evolution that we think of as the noise, and then try to see how this holds. But we haven't got to that point yet. But yeah, definitely connecting to experiment, is something that we want to do. The thing is that extracting these quality parameters is the really difficult thing. Mm-hmm. So this Q, that is the difficult thing. But we already can do some analysis, like in this PRX paper, I think somewhere. So the analysis, for example, that we did in that paper, surely we could already apply it to to some experimental scenario, like with some real experimental data. But yeah, we haven't done that.
You haven't done
specifically
it. Okay.
yet.
Okay.
Yeah.
Okay.
Yeah.
But it's free now. You know, some machine is
Yeah.
free. Yeah. And you work with Shisheng, then he
Yeah,
can
yeah.
access all IBM machine. You know?
Yeah. So Shishan is doing trying to apply machine learning techniques.
Okay.
To learn or to get some insight of what the underlying noise would be. But yeah, definitely Shishan could also look at doing something like that. Yeah.
还有问题吗? Any further question? So if not, let's thanks Pedro again. Okay, thank you, Pedro, for a nice talk.
Thank you very much.